Welcome to this evening's stream. We're going to be doing looking at Xilinx XDMA, hardware driver, the driver software, how we interact through it through Python to be able to do what we want, and then we're going to be looking at the Xilinx virtual cable, which will allow us to generate our own interface to be able to do custom JTAG commands over PCIe, which will allow us to debug a microblaze through the PCIe connection, not require a JTAG interface that is common to this design. So yeah, let's tackle it. So Xilinx DMA is the XDMA is Xilinx direct memory access, and we use this. This is what the PCIe module is called that allows us to do DMA transactions. So let's go take a step and look at the hardware. Yeah, here we go. Not the one. Here we go. So we'll ignore most of that right now. So right here we have our DMA bridge subsystem for PCIe Express. Let's look at our configuration for this real quick and make it a tinier box so you can see. Not that tiny. Okay, so we're going 4x. Yeah, these are basic features. We haven't really changed that. What we did add was a PCI to AXI master, and we make it 1 megabyte, and we give the transaction. This is like it adds this value to your address space, so that when it writes over AXI it acts this. I'll show you how that works later. And then we have DMA. And the DMA, we have one write channel, one read channel, and we have width and AXI ID width and stuff like that. And that's pretty much it for that. So now let's look at these two buses. So right here is the DMA bus. So that DMA bus goes directly to the Smart Connect, which then goes to our DDR right here. So we go to the address space. We're looking at this right here. And we have 64 bits of addressing, which is quite a lot. We probably don't need 64 bits of addressing on that guy. And we have half a gig of DDR. Pretty sure this is a full gig. I did a full gig on my design, right? I'd be surprised. Yeah, it's a full gig of DDR. I'm not sure why this is a 512. But that's okay. This is design is not the final design. I will implement this in my final design for a gig. For now, half a gig is good. And then we have this AXI light. Remember, we updated to 4000 or 40000. So we have 4 devices here, each taking 64K, and they're closely knit together. We have the debug bridge, which we'll talk about later, GPIO, and quad SPI. And let me just talk about the GPIO because we'll be accessing that. So we go here, we go to this interconnect, and one of them is a GPIO, and we are connected to the model, which is this value right here. And we're connected to the version, which is a 1. And we'll read those through the PCIe in a second, so you get a good understanding of that. And we'll read it. And so right here, this other device on this is the microblaze. So the microblaze is both. So the microblaze and the PCIe are both masters to the DDR over here, and they're both masters to this interconnect, which is connected to GPIO and quad SPI and this debug bridge, which is part of the Xilinx virtual cable. So this is good. We have the hardware, super easy to implement, wasn't a big deal whatsoever. So let's go look at the driver software. Let me open up a Chrome tab. And we can go and remove my, oh, that's not one. Go ahead and remove my bookmark bar. Not what I want. Oh, it's because it's on this front page. So we want XDMA driver, Xilinx, sure, GitHub, and we want the GitHub location. So XDMA Linux kernel. Is this what we want? Yes. So this has a few directories. It has the kernel module, supporting files, includes, and some bunch of tests that we can run on our device. And you have to follow the instructions to install it. It wasn't that hard. So I was thinking, so I was going through and I'm like, I wanna see if I can write my own driver in Python and just memory map this sucker. And just after looking through this, I was like, I think I'm just going to try to use their driver software, see how difficult it is, because this was overly complex and I wasn't sure about all the functionality it supports. And so going through this, trying to read through this to read the different functionality it provides, and there's a virtual cable here, but they don't talk about how it works otherwise. So I went through and tried to get this all up and running, or tried to see if I can implement this myself through Python, and it was a no-go. Bad idea. So I went ahead and I downloaded this to my device. So where is right here? Okay, I guess. So which best? So yeah, so right here, DMA IP drivers, and we installed the XDMI driver. So what this ended up doing, I know, let's go run one of the test things there. So if we go there, XDMA, xkernel test. It's only has part one. Okay, so we have, I think it's load driver. So if we do sudo load driver. Okay, so we already have it in use, so we can't remove it. That's fine. So let's go back to CD. Let's go to dev real quick, and we do this. You notice that we now have a bunch of XDMA controls right here, right? XDMA this, XDMA control, a bunch of events, XDMA this, user, and XVC. Never really explained. So I've been trying to learn how to access this, and the best example I got was so you use this user for the we use that channel for the AXI Lite interface right here. So we can read and write to the AXI or the XDMA user, and it'll do transactions over this Lite interface. And then for this is host to client, or host to client, and client to host. So this is for reading, and this is for writing. And we can do that to do transactions, and we can memory map those, or have a file and then write to those. And I've been trying to figure out how to use this transceiver one, because I mean, we could read and write to it, but what does that do? Maybe we could try that real quick. I'm kind of curious. Maybe we'll try that. But like, I've been looking in the software here, and I mean, if we type in XVC, right? It has these addresses. The make file has a offset here, and I guess we just write to those addresses. I don't know. I can do that on my own, so I'm not worried. So I'm not sure what their plan for that was. This is also on a completely different driver, not the driver we're looking at. We're looking at the XDMA one. Yeah, I mean, we could look at this. Oh, so this is just IO write. So they're just writing values to this thing. Transceiver magic, XVCD, bar offset. Yeah, I don't really know what's on there. But yeah, I'm curious. So let's go back to Python land. And so right now I can open my XDMA user file, and I can write to addresses. So if we want to write to the GPIO, we can read from the GPIO. We get this. So if we remember, that GPIO was connected to this model right here, 46, 49, 54, 45, and when read, we get ETIN. And then the other one, this version, is 1. To read that, we go to this address. So we can read the user, which is really easy. We just have to do this. So now let's go close this file. I think it's what, fd.close, or is it os.close fd. Okay, then let's go here, and we want to do, what was it titled? We want to do client to host 0. So client to host 0, right? We want to do fd.pread, or no, we want to do os.pread fd. We want to do 4 at the beginning of the DDR. Okay, and then let's read 24 bytes. Okay, so that's cool. Enough that let's try writing memory to it. I'm gonna do not that, but 3121. Cool. Targets, tag targets. Oh, we can't access the microblaze because it doesn't have a JTAG chain. Oh well. So that's what the if I had another design ready to show you. But this is what the DDR says. I've checked it, so we can read from the DDR. And let's see, can we do FW read only, or like write only. FW, we want to do host client. We want to do what, os.p_write. This is me just guessing, so don't trust me on this. I guess let's go look up at what p_write does. Linux OS p_write. What parameters do we need? So we want the file, a buffer, count, when I was to read. I guess you can read into that buffer. So let's go back to here, right? Now here. So what we want is a buffer. So called data what not equals byte array. Not sure if I have to capitalize that or not. Actually, Python list to byte array. Create a byte array from a list. Byte array. That works. So make a list. 0, 1, 4, 5. Can I make a list like that? How you made a list? How you made a list? And can we do data b equals byte array data? You happy with that? Let's print out data b. So we have a byte array. Cool. So let's do os.pwrite. We're going to do fw. We're going to do data b. Data. We're going to do 1, 2, 3, 4, 5, 6 bytes, I guess. And then we're going to do it at that location. And return 6. Okay, then let's read it with the other one, right? Go! Sweet. I wish I had another way to verify it on the other system, but it looks like we can write and read to DDR with our DMA driver fairly easily. Sweet. Okay, so our next concern is we want to debug. So we'll go here. So we showed you the hardware, show you the Xilinx driver, show you how we can interact with that through Python fairly quickly, high level. It's very useful, very simple. And I mean, in the future, maybe we'll show more complex software allowing us to do testing over it, but seems pretty solid so far. So our next thing, we want you look at the Xilinx virtual cable. So the Xilinx virtual cable is basically you give a you create kind of a TCP port or UDP port, whatever, where raw JTAG data is sent to this port, and that port forwards it to a JTAG device somehow, some way. You get to decide how that information is forwarded. And so for here, we're using the debug bridge. So let's go here. So we're using something called the debug bridge. I remember we are not want a backup one. I didn't think that was interesting. Actually, yeah, we'll just keep it there. So what happens is we have the PCIe device over AXI Light interface through this interconnect, through this port, writes raw JTAG data to this bridge. This bridge then sends that JTAG data to this microblaze debug module, and then that microblaze debug module is connected to the microblaze. So this allows us to connect our microblaze to like a GDB server or using the Xilinx SDK over the internet and through PCIe. And let me show you how we're going to do that. It's fairly straightforward, not hard at all, and I have some basic software that works through it. So that's pretty much it. Basic configurations. For this, what I did for this one is you want to do an external BRAM location, and then for this one I did AXI to BScan. There is a PCIe to BScan, but that's only for ultra scale devices. But this one should be fairly straightforward to do. I made so it uses 2, and you can have multiple devices on there for debug cores and whatnot. But the hardware, fairly straightforward, fairly easy to run. The software, so let's go look at the software. We want to look at the boom. So they have an example of the Xilinx XVC for the Zinc device. It's on GitHub right here. So we have a Xilinx virtual GitHub thing, but this is for putting it on a Zinc 7000. So we're not putting this on a Zinc 7000. We're putting this on our own Linux i5 device. But they have some other source here. This is a little bit more complicated. If you go to their XApp answer right here, this is actually very simple C code, and it explains how it goes. So first, let's go down to the main. So it creates a main. What it does is it picks a socket, determines the socket, gets the address and whatnot. Fairly basic things. And then once it's connected, it calls there we get that. There's somewhere. What's the function? Maybe it's this accept command. New FTD. FTD set. Okay. So at some point it calls this function handle data. So where is this handle data? Where's the other location? So there's where it handles data. So it handles data. It gets our input buffer. This is our input buffer, and this is our output buffer. Looks at the first 16 bits. If the first 2 characters are GE, it sends back a string. If it's SE, it's doing a it wants to set the clock rate, set the T clock rate, and if it's SH, it wants to do a shift command. So yeah, so it's this one. GE is actually get info. SC is actually set TCK, which is set the JTAG clock, and then we have the shift. And if it goes to the shift, we go down here and it writes the length, the TDMI, the TMS, the TDI, and this control bit to memory addresses on the device, which is the first 4 addresses. And then it wants to read out the TDIO, so it waits till that control bit flips again, and then it reads out the TDI, the 4 TDO bytes, and then it keeps repeating until it gets done. And at the very bottom, if it's not a 32 bits but less than 32 bits, it has a little protocol for the very end. So that's kind of how this works. So I kind of wrote this up in Python real quick. So let's look at that. So Python, here's our server. This is the port we're using, our input buffer, boom, 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 accept the location, why we have the accepted location. When we receive data, we're going to look for get info, and then we're going to return this string. We're going to look for set clock, and we're just going to return the data so it knows what we set the clock at. We don't have a clock, so it doesn't really matter. We don't care about the clock speed, so we kind of just ignore that command. We just give it back the data at once. Next, we have shift. We collect the length. We collect the TMS data, the TDO data, and we just write zeros, and then we return this. So I kind of wrote a blank driver, and now we need to actually send this to the processor, right? Or send this over PCIe. But let me show you how this works real quick. So we'll go to PyTest. And we're going to do sudo python XVC. So now it's waiting. Now we go over here. We're going to disconnect. And we're going to do connect dash XVC dash URL TCP address and port. We pick port 4000. So I hit enter here. Right? And we'll see over here, it's going to start going crazy. So we got the get info command. And then it does a bunch of these. So let's see, let's go through this. We have get info, we transmitted the data. We received set clock, we transmitted the speed it wants us to set. We received shift data, and it wants us to do a 43 bits, right? So this is the length in bytes or in raw bit. This is the value for it, 43, and then it wants this, so that's gonna be 6 words, or at least 6 words. And this is the data we returned, or six bytes. These are the bytes we returned. And then we have a bigger shift command, which is 1070 bits. You see how these bits aren't lining up correctly? And then our data we returned. Then we have 46.6 again, then 1031.33. Then we have like an 8.1, 43.6. So yeah, kind of some odd sizes. And yeah, and the device is constantly checking to see if there's new devices here. So let's go. If we type in JTAG targets, what we'll see is we have a Xilinx virtual cable at the address with the port. And we're shifting all zeros. Because we set this up to return all zeros, that's what we're seeing. So let's go ahead and close this out, and then let's have some fun. So we're gonna do so let's pull up this virtual cable thing over here, and then we're just going to kind of write this this for loop out in Python. So NR bytes is going to be byte. So yeah, let's go. So yeah, let's just go through and write this out. So we have bytes left equals, well, we keep the capitalization, but I might be able to copy some things and just play around with them. NR bytes. And then we have what, bits left. It's going to be length. And then we have, we don't really need to worry about the byte index because I already grabbed these things. I guess we could do byte index and we might move forward. Index equals 0. And then we have TDI, TMS, and TDO equaling 0. We already have TDO set up and the TMS, so let's not worry about that. Okay. So the while bytes left is greater than 0, let's do something fun. Don't worry about those ones for this implementation. If bytes left is greater than or equal to 4, so first thing first, let us grab our memory. So we're going to import OS, and so we're going to want those commands that we had over here. Okay, so we want to do this command right here. Copy. So first we want to do we're going to do fwrite and fread user, and this is going to be write only, and then we're going to do fread, which is going to be read only. And let's go ahead and open this at the beginning, and then we can close them at the end. That seems like an obvious thing. Hopefully we can open the same memory address and just have those going. So going back to this code, so we just have these pointers, right? We don't really have addresses. I mean, well, it's right here, which is great. This struct actually points out the addresses quite well. So what we want to do is we want to do os.pwrite, and we're going to do fwrite, and we're going to want to do I don't want to do it as a word. I'm not sure how we do that per se. So maybe we want to do how do you write an int? Yeah, I guess I could do a read write. Let me see. What is os open read write? What's the read write flag? Maybe we can just do a read write flag. Open for read and writing. Let's try that. Try that out. Now I'm just kind of curious of how we can write data. Also, we have to write it in the correct endianness, right? Because the least, it's going to be the least significant byte first. So, I mean, could we just, what happens if we just want to write this? Is this just going to throw an error? So let's go play around with that. So let's go over here to os.close fd and close fw, right? And then let's open the user one. User one, and we want to read write. So we're going to open it read write. And if I do os.pwrite, pointer right, and just do write, op. Let me see, because they just do a write and then they put the thing there because it's already done that. I assume the other functions you could do is seek. You would do os like seek. So I mean, if we do os seek fd0, so it has no seek. Oh, is it lseek? I think it's lseek. Expected 3 arguments. Okay, what is Call it here. Where is it? lseek files. FD offset whence. What does whence mean? Okay, repositions the file offset of the open file descriptor associated file descriptor to the offset according to the directive whence as follows. The file offset is set to its current location plus the offset, so we want to do seek set. I assume that's gonna be like os.seek set, right? os.seek set. Legal seek. Okay, we'll just try os.write. Right, so we're gonna write fd, and I'll write a 20 to it, right? So we want a byte-like object. What is the syntax for byte? So can I go like b/x20? Come on, can I do something like that? Oh, it wrote 4. So if I do os.fread, yeah, mmap might be easier. fd, comma, let's read 4 bytes and let's read it from address. That seems not what I want to write. Interesting. So let's do our own data array, right? Let's do, we want to do 20 for 32 bits, 0, 0, 0, boom, and data b equals byte array data. And then let's do write because I know where that one's going. Data b comma 0. 4. Read it now. Oh, 20 in ASCII is, so let's do hex. Hex that. Do like int, or is it like dot int? Oh, how do we do it here? Oh, we want to do int dot from bytes, comma bytes order little, comma signed equals false. One, 2, 3, close, 4, 1, 2, 3, 4. Byte order. I do not like about byte order. Oh, let's get rid of that one. Do comma byte order equals little, right? That's sign. So, and let's go ahead and remove the hex. So we got 32. Okay. The best way to write that is kind of weird. Now let's see if we did like that, or no, We just do, and then we go, where's that right? Right, data 0. So we wrote 4 bytes, so I guess we have to write 4 bytes. And then we look at it. Oh, it's a bunch of zeros. Oh, it's filled with zeros. What's a Python make byte array? Why are byte arrays so difficult? Maybe there's got to be a simpler way to do byte arrays in Python. And then we do size. We got a bunch of blanks there. Yeah, it looks like I have to create a list beforehand. Okay, we can do this. So let us look at we do like this. And then we do write 4, and then we do a read. Let's put that in hex so I know what's happening here, because I don't understand that otherwise. Oh, and then it looks like it wrote, just extended the memory a little bit. So, I mean, then we do if you write to 4, and then we read it. Okay, so yeah, it looks like we're gonna have to fill in the entire word. So Python C types. See if that's useful. Python C types. C underscore. Does it have a way to go to a byte array? Because the input requires a byte array. Can I type like byte? Yeah, I don't know. Byte array looks pretty straightforward and it's not a big issue. Oh, bar values. Okay, well, let's just get this working with byte arrays real quick. So we want the length right. Length right going to equal and this is the smallest bit, byte. Ooh, do I have to reorder bytes? That could be fun. We'll figure that out. Well, it comes least byte significant, so I think we can just get away with that. So, we're gonna do byte array because I'm lazy. Length right. I guess we could just do sign right there. So yeah, I'm gonna do length right. Oh, it's gonna be at that address. And now we want to do the TMS right. TMS is going to be at address 4, and we just want to do TMS. We want to say byte index byte index x plus 4. Yeah. Hopefully that works, because we'll find out otherwise. I'm going to do TDI base 8. Let's verify these addresses. Create that struct right there. I'm pretty sure if we go to the driver, they have the addresses in the driver. Driver right here. 8, 4, 12, 16. Okay, then what we want to do is we want to do control, which will be a 1. 0, 1. Control right. Then we want to go to address 10. Do a control right. And then we want to do like a little while loop. And os.pread fd 4. And we're going to store this in output. And we want to do while output byte 0 does not equal 0, 1. And then we just keep reading that. Boom, boom, boom. And then we want to read TDIO. We have TDI byte equals read of C. And then we want to bytes left equals bytes left minus 4. And what about byte index? Byte index equals byte index plus 4. Right here. And we have a bits left equals bits left. And it's 32. Okay. Cool. Else. We're going to do the same thing, except we're not going to care about those because those are worthless. We want to do bytes left, 1 byte left should go forward 1, and bits left should be written here. And here, that's a good question. I'm not sure how that's going to out. And I assume we're just going to do 0, 2 bytes left, type of thing like that. And we want to just end of these, just print out TDO. And do that. Do that. Save this. Hopefully this is updated. And see what happens. Hopefully it crashes and burns. Oh, we never close it. Interesting. So we do a shift. It seems like we're waiting. So let's go ahead and kill it. And let's print out. Ooh, probably do a print of the outputs. Make it realistic. Let's put a time.sleep in there, right? Let's sleep, what, 5 seconds? Time is not defined. Oh, did it import time? Did that not go through? Let's try again. Time's a slave. Save is a little bit slow. Okay, that's what we want. It went down. So, oh, does while it equals 1. That's what we. So yeah, let's go ahead and kill those out. O is not defined. Where is O defined? O bytes. Item assignments. Okay, so it doesn't how how do we do this then? So we want to assign these values. Any idea how to get through that? The copy. Why is this so close? We never updated. Well, what if we just did this? What if let's see what happens here. Maybe it's just it will just ooh. Doing lots of commands. That's good. So let's go ahead and not print those out. Not print that out. We want to print TDO, and oh, we're returning TDO. Interesting. Well, a lot of data, but let's see what's happening. Targets. That is a lot of text. Unknown error closed. Okay, so So let's debug this. Let's put a time delete here of 20 seconds, and let us print these values, right? That let's print the values here. So let's print length right, because yeah, and I wonder if we're doing the order wrong, because bytes are definitely that order. So doc nav design. No, I want the debug. So let's find the debug bridge. Debug bridge. Where's the debug bridge? Sure, why not? Design of these cores, product specification, register space. They don't say what byte or bit order it is. So interesting. Maybe we can go both directions. Well, I'm trying to make sure I got the Indianness right. I feel like I have the Indianness right for these commands. Do I need to flip the bytes in these commands? Because it makes sense in here if you have bytes left, it's just that many bytes left. I'm not sure what happens when we do the extra, but it should be okay because the length right. But they don't look like. Oh, they do the bytes one by one, don't they? Or yeah, I wonder if we have to flip the bytes for it, because they're expecting the bit order to be on the left side just because they have how they have it written. Python array reverse x reverse indexing. Okay, so we try it that way. Well, let's print out everything real quick. Um, and okay, that seems did I put my sleep as too long? What was that run twice? Oh, it's because we need to zero these out. Or we need bytes left. Zero, zero, 0, and 1. Okay, so let us remove this and our print statements. We may have to reverse it still, but okay, so that's good. Okay, so let's see. Anything, I think we might have the byte order in the wrong. Yeah. We run it again. I think we break it. Oh, is there a second shifting? Oh, we may have to. Looks like there's another command. Unfortunately, the VS Code is not connected to my. It's not running off my Linux machine. Um. So if the only thing I can see right here is that we have multiple shift commands inside the same packet. We have like shift, shift, shift. So we need to process this and send this as one packet. Oh, that sounds painful. We could do that. I just need to have the Python handle that better. The best. Okay. I'm still not sure if the byte order is correct. I could maybe. That's gonna be. Well, let's try. We try reversing it and see what happens. Byte order. Because this code doesn't reverse, just writes that there, writes the TMS, it writes the buffer. Matters how it reads those, because I'm not sure how it reads those, because it may be memory copying those in a different byte order. So what we want to do is we want to read multiple shifts. And the while loop do while one. So it's doing a while one. When does it actually? Oh, they have a break right there. They do break, but is that breaking out of that while loop? And we write the value. And when do we break out of this while? We have returns. Return 1. Return 0 after we get out of there. There's only one break, right? Code is weird. Let me see. Here's the break. Break there, break there. Inside that statement, though. I don't know what's going on. Yeah, we'll have to look at that. Yeah. I'm just trying to figure out. So this seems to be working. Not sure about the byte order, but it's hard to tell at this point. What else could we do? Because it's breaking here when it does that. It's breaking there when it does that. Then it goes to the other thing. But here it does a read. It breaks, but it's already inside this while loop, so it should just break out of that while loop. And repeat. We go back to here. This is just the confusing part where we have multiple shift commands. Multiple guess we'll have to put a while loop here as we go through the data. Huh. Okay. Now that I think about the bytes are probably correct because the bytes on the left are going to be the newest ones, and when we run out, that's where we're writing to. Because they're not doing any byte shifting, right? How do they do? They write the bytes and it automatically. Yeah, they're not even doing any shifting, so they might. So this must reverse the byte order as well when they do the M copy. Okay, so I think the only thing is we need to handle multiple shift commands. So let's do right here. We're going to do command right here, and I want to do 10 plus the NR bits plus 2, right? And then I want to print command. See what happens if I try to run it like that. It's probably going to throw an error. Reads across the thing. Let's see what happens. So it gets there. So we need an index. When we do this, we want to say index equals 0. I want to say index plus this, x plus this. Yeah, and index plus that, index plus that. To do index now equals crazy guy. And then we want to do index plus 2. Index comma index. Okay, cool. And I guess the quick way we do is just stick a while loop right here. While command equals sh. All those indexes. And we take this whole thing, put it in that while loop. So now let's do multiple commands where it updates the index. We're crazy. Let's see if it works. Oh, do we rewrite the data? We rewrote the data. That's bad. Let's change this to send data. Something as simple as that. It looks like it's doing that. Targets. Device configuration unstable. That's great. Ooh, so the question is then, do we add these all together and then send them? Too many open files. That's another thing. So at the end of this while loop, we need to do os.close fd. So could be the issue? Do we need to rearrange bytes? So close, so close. So let's try a disconnect, right? And let's try reconnecting. I don't think that's going to help, but see what happens. We switch this byte order? I don't know. No. Error device configuration on. So I wonder if it's so we have a few issues. It could be the multiple shift command, or it could be we have the bytes in the wrong order. I don't think it's the bytes though. I mean, we could try to switch them for fun, see what happens. Um, okay, so let us try flipping the bits, and I guess zero padding these guys. So kill that real quick. Um, yeah, that's the easiest way to do it here and here. And I don't think this is going to work. It's going to hate us for that. Okay, so we're going to have TMS raw is going to equal a byte array of 4. And we're going to have TDI raw, which is going to be a byte array of 4. And go ahead and just, yeah, TDI raw, TMS raw, TDO raw. And how we want to do this because of depending upon the slot, right? What we want to do is we want to say we do 4 minus 4 minus bytes left of 4. That kind of gets like the end. And then we want to so this gives us the end values. And then we want to do TMS like this, but bytes left. TDI, TDI raw. Okay, and this one. Indianness, right? Python, if this works, I like you a lot. If it fails, I do not blame you. TDO raw is not defined. TDO raw get used. TDI, oh, it worked for a good portion. Flipping those bytes around. Okay, so attempt to assign sequence of 4 to extend slice of size 1. There's no way to go like what, 0 to byte left, right? Can't do that. Oh. So let's print these to understand what size is going on here. Woohoo! Magic of Python. Go. I'm sorry, I'm doing nasty things. Don't blame you. Can I just do can we just do byte left there? I mean, what happens if we don't read a full 4? Tell me, tell me. Um actually, can we is it definitely returned? Definitely 4 bytes right there. Can we do 0? Attempt to assign sequence of size 2 to extend slice of size 1. We print bytes left as well. Didn't print what I wanted to, so maybe it's not done yet. I see a little bit of an issue. There are 2 left. We're only getting 1 out of that. Oh. What is 0? I want to see if this is only producing 3 because that would be bad. So let's see these two flip back and forth, see what we get. Because byte this right here, byte index plus bytes left, byte index minus 1. Not what I want to see. Okay, so we're having an issue here. So minus 1 is not getting that guy. So let us print TMS as it's seen here. Figure out which ones we are writing in. Okay, so that's what we're getting. So I think we're getting these 4 written the other direction. So that means what we want byte index minus 1. Okay. I did the backward thing right. Um, ah, I don't like these solutions. Ah, okay. So we may just need to change Indianness or byte array, and maybe we just do it at a. Okay. So let's forget about this nasty opposite indexing system. Okay, and what we want to do is here, we want to flip around all of those. Would probably be the easiest way. I agree. Oh. The problem with this. We need to do 3. Oh, I've seen this before. I have this code. Here. Let me pull it out. Ugh. Okay, so that is only doing 16 bits. We want to do that much. And we're gonna this real quick. Flip the bytes. All right. That works. That's a solution I can live with. That right. Cool. Let's see how well this works. Item assignment. How do we do it in the other place? Oh, do we need to make it a byte array? Byte array. I can do that. I can do that. Are you happy with that? Let me see. Attempt to assign bytes of slice and to extend slice of 2. Okay. May not be as well as we hoped. Yeah, we may just have to end it today, and I will play around with getting this to work so we can do some Indianness change. Okay, well, thanks for watching. I will post this. Hopefully it's not too long. It's only an hour and 27 minutes. Oh well, we'll keep playing around with it. Thanks. Night.